How are you guys? I welcome you to this series of lecture, and the first topic that you look with me is electrolysis. Now, like I earlier mentioned, with me there are two components that we look at. The first component has to do with electrochemistry, then the other component has to do with thermochemistry. So first I'll start with electrochemistry. Now, in trying to understand what this is, basically, like you can see from itself, it says electro. Okay, let's define, or let's look at what basically this is. So electrochemistry is a study of chemical processes that produce electricity. So you have electron, then there's electricity that is produced, and that electricity is produced by movement of electrons in a redox reaction, meaning you have an oxidation reaction, then you have a reduction reaction. So two processes are taking place, and I'm sure, as you are aware, you know that by now one definition of oxidation that you get is that oxidation is basically the loss of electrons during a chemical reaction, either by a molecule, an atom, or an ion. Then what you normally get is that the oxidation state of the molecule will increase. So in electrochemistry, you have two chemical reactions that are taking place. One reaction is an oxidation reaction, and the other type of reaction is a reduction reaction. And then when you combine these, this is normally referred to as a redox. So you have RED meaning reduction, then OX meaning oxidation. So it's a redox reaction, meaning in this case, when you talk about oxidation, it's basically saying transferring of electrons from an atom to the other, meaning there's loss of electrons. Then when you go to reduction is the gaining of electrons by an atom. So you've understood that in the first instance, one atom has lost electrons, so meaning the other atom will gain the electrons, and the ones that gain electrons undergoes a process what you normally refer to as a reduction reaction. Then reduction is just basically the opposite of oxidation, and in this case the oxidation state of a molecule, an atom, or ion will reduce. So what you get here, it gives you a schematic diagram on a redox reaction. So you have A with oxidation state 0, then you have B with an oxidation state 0. So if A undergoes oxidation, what it means that A will lose electrons. So when the electrons are lost, it will gain a positive charge. So what it means that its oxidation state has increased, because the charge on a particle is equivalent to the oxidation state of an atom. Then at the same time, if you have B with a charge 0, it gains an electron. What happens that it forms a negative charge. A negative charge, it means a reduction in the oxidation state. So basically this gives you a preview. So what you have is that when you talk about electrochemistry is just basically generation of electricity through redox reaction. Let's look at some terminologies or some terms. Now, like I always advise people, is that for you to understand the language, you should understand the terms that I use. Let's start with what normally means. What does it mean when you say spontaneous reaction? A spontaneous reaction. So it's a redox reaction that occurs without any external help. It just occurs on its own. For example, if someone says he is a spontaneous person, meaning he can easily do things without anyone forcing them to do it, then these reactions will take place in what we might refer to as a galvanic cell. We will define what a galvanic cell, or look what a galvanic cell is as we proceed. Then there is a non-spontaneous reaction. A non-spontaneous reaction is more or less like the reaction doesn't want to take place. However, you want it to take place. So what do? You force it. And in which sense you can add an external electric current so that the reaction is forced. Then this normally takes place in an electrolytic cell. So in a galvanic cell you have spontaneous reaction, then electrolytic cell you have non-spontaneous reaction. Then in electrolytic cell, these reactions are also referred to as electrolysis. So spontaneous, the reaction will take place on its own. Non-spontaneous, the reaction is forced by an external force for the reaction to take place. Okay, we'll look at this a bit later, but this gives you a diagram on what it means when you have a galvanic cell. This is where a spontaneous reaction goes through. Then you have an electrolytic cell. This is a non-spontaneous reaction. Don't worry about some of the details of the diagrams. We'll tend to define some of these terms as we proceed. Let's look some definition. Let's understand the language. And you probably be aware that as we proceed or as we move during this lecture, you will discover that there are some terms that will be used. So before we start using the terms, let's try to understand what each and every term that we'll be using would definitely mean. Let's define what a cell is. Now, in electrolysis, a cell is a compartment where a spontaneous reaction or a non-spontaneous reaction will take place. So basically, you just have a compartment where a spontaneous or a non-spontaneous reactions do take place. Then you have electrodes. An electrode is a surface where oxidation or reduction half reactions occur. They may or they may not participate in a chemical reaction. So if you have what you normally refer to as an innate electrode, basically this does not take place in a reaction at all. So anything that is innate, it is inactive. Like for example, you have innate gases in a group 8. Most of those gases are actually not reactive. That's why they are called innate gases. Let's look at an anode. An anode is an electrode where oxidation occurs, as electrons are lost by some species. So an anode oxidation takes place. Then at this point there is loss of electrons. Then there's a cathode. A cathode is an electrode where reductions occur, then the electrons are gained. So at an anode you have a species that loses electrons. Then at the cathode you have species that gains electron. Now in the next slide it gives us an overview on how a galvanic cell looks like. Now remember, we says in a galvanic cells only spontaneous reaction will take place. Then this reaction does not need any form of help. They will just happen on their own without any help. Then the change in energy is less than 0. Let's not worry about this for now. We'll worry about it as we proceed. Now let's look at the schematic diagram of a galvanic cell. There are some features that you have here that you personally need to understand. For example, you have an anode here. An anode, that's where oxidation takes place. Then an anode is negatively charged. Then you have a cathode. A cathode, that's where reduction takes place, and the cathode is mostly positively charged. Then the movement of electrons will move from a negatively charged, you have an electron here, so an electron will move from a negatively charged to a positively charged cathode. So this tells you the movement of electrons. So the electrons will move from a negatively charged cathode, it goes through that way to a positively charged anode. Then inside here is what you normally refer to as an electrolyte. An electrolyte, what it does is that you have charged particles that are capable of transferring electrons. Then you get what you normally refer to as a salt bridge. So when you get a salt bridge is the one that connects two compartments. So you have this compartment where there's an anode where reduction takes place. Then you have this where oxidation takes place here. Then you have this compartment where reduction reaction takes place. But now what you understand is that in a galvanic cell there is a transfer of an electron. So more or less like you need to have a complete circuit. So a salt bridge will serve there to help the circuit to be complete. So in here also you have electrolyte that allows the charge to go through the liquid, and it goes round, then it goes round, and then you have a complete circuit. So if you connect a bulb here, what you expect to have is that the bulb will lit. The reason being is that you have a complete circuit, and that complete circuit is achieved by the help of a salt bridge. Okay, so you have two half cells. There's this half cell here and there's a half cell there. So there's oxidation will take place at the negatively charged anode. So this is where oxidation will take place. Then reduction will take place at the positively charged cathode. Then a salt bridge acts to complete the circuit by joining the two half cells together. So if a question is asked, what's the purpose of a salt bridge? The salt bridge is a parameter that is used to connect two half cells. So now in your sense, it is quite important or significant that you may know how to draw a galvanic cell. So during your free time or you are studying, you can sit down and try to draw this from your memory, because sometimes some of the questions that comes in exams, it will require you to draw this schematic diagram. Okay, so from the galvanic cells, there are two half reactions that we get. So at an anode, we get oxidation reaction. Then you understand oxidation reaction is a loss of electrons. So meaning you have zinc, which is a solid, it loses electrons so it undergoes reduction, oxidation reaction. Then at the cathode, you have copper, which is in liquid form, it gains electrons and it forms a solid. So you have S, a solid. So here you have a solid, loses electrons and gets an aqueous medium. Then here you have an aqueous medium, it gains electrons and it becomes a solid. So even when you're drawing the two half reactions, pay particular attention to the details. These state symbols are equally important. So if you leave out this, you are definitely leaving out some scores. So when you're writing or you're studying, try to understand. So for oxidation reaction, you have zinc in a solid state, loses an electron and gets into an aqueous state. AQ means aqueous. Aqueous is water. So this is in water state, then two electrons are lost. Then when these two electrons are lost, they are gained by copper. So when copper gains two electrons, this is a negative charge, this is a positive charge, it gets neutralized and becomes a solid, and this is a reduction reaction. So you can write the overall reaction. What you have is that on this left hand side there is 1, 2, 3. So you can have the overall reaction will be, sorry, I'm using a mouse to write, so my writing will be very, very bad. Then you have this. I don't have a touch screen. Please don't forget to indicate the state symbols plus 2 electrons. So what we're doing is that we are writing, sorry, I need to just give me a minute. So what we're trying to do is we are writing everything that is on this side and putting it here, because we are writing the net equation. Then we have an arrow, then we have everything after the arrow here, including the state symbols, and put it on that end. So when we have zinc, so we can start with copper. Copper this side is a solid, then we go to zinc ion, which is plus, then zinc this side is in aqueous state. The other important thing that you need to understand or note is that positively charged ions or any ions only forms in an aqueous state or in a solution, plus 2 electrons. So now what to do is that there are electrons here and the electrons here, so these electrons will cancel each other. So the net equation that will result is what you have or what you're seeing here. Alright, let's go to a cell notation. How do you write the cell notation? The cell notation is written with an anode on the left, meaning you have an anode half cell reaction here, then a cathode on the right, so the cathode will be here. Then the other significant thing is that you have a salt bridge separating with two vertical lines. So you have two vertical lines. So you have an anode and the cathode separated by two vertical lines. Let me see if I can try to. Okay, so you have the reaction on the anode, right? Then separated by two lines, then you have a cathode. This is the reaction that's taking place at the cathode. So this signifies a salt bridge. Perfect. So this is what you have. You have an anode half reaction, then you have a cathode half reactions. So now from these half reactions, you have one single line. Now this is a double line here representing a salt bridge, then a single line. A single line represents an arrow. So in this case, you have this is represented by a single line. Then you don't write the electrons. Then please also note that when writing a salt notation, the state symbols have to be included. So in this reaction, for example, you have zinc solid giving you zinc 2 plus aqueous plus 2 electrons. This is the reaction that is taking place at the anode. So if I'm writing a salt bridge from here, I'll just write zinc in a solid state, then slash one line representing an arrow with zinc in an aqueous state like this. So you have a half reaction at an anode. Then you can draw two lines representing the salt bridge. Then you go to the reaction at the cathode. Now from here you understand that the reaction at the cathode, you have copper. Once again, I ask for forgiveness. Please bear with me. I'm trying to use the mouse to draw, so my writing will be very bad, but I'll try to do my best. So this is in aqueous state and this is a solid. So if you're writing the half reaction at the cathode, you start with this then end with this. So now what you get is that you have copper aqueous, then with a line, then copper solid. So what you have is that this is oxidation reaction. So what you have here is oxidation reaction. Now from our definition, this is reduction reaction. So from our definition, or one key factor that you can use to help you memorize this is that in an oxidation reaction, there's an increase into charge. So you're moving from 0 charge to +2. So this is oxidation reaction. So oxidation reaction will always be on the left. Then in the reduction reaction, you are moving from 2 to 0. So meaning there's a reduction in the charge, meaning there's a reduction in the oxidation state. So what you can do is that during your free time, you can actually sit down and try to do practice these using different examples. Then now what you get also is that when you move from left to right, it shows you the movement of the electrons, like what you have here. So in short, what we're trying to say is that zinc loses an electron and form a zinc 2 plus an electron. Then copper 2 plus gains that electrons and form copper solid that you have there. Let's go to standard reduction potentials. Standard reduction potential, these are standards that help us or give us very useful information to determine which reaction will undergo reduction. So reduction potential basically will just tell you the likelihood of a reduction reaction. So these are the values that you have. So you have E0R, so meaning E0 it means it's a standard, then RED means reduction. Then this is like more like a volt, electron volts as well. Then they were done at in water at 25 degrees. So you have standard potentials of different reaction. Now what you should understand that all these reactions are presented into a reduction half reaction. That's why it is called reduction potentials. So all these reactions are in form of reduction reaction, in the sense that, for example, you have this is gaining an electron, this is gaining an electron, this is gaining an electron, then all of these have aqueous, and you have a liquid. So this is gaining these electrons, this is gaining these electrons, this is gaining this electron, this is gaining this electron. So in most cases, in all these reactions, all the elements are gaining electrons. Then you have the values or the charges that are associated with it. Then there's for example, if you look at this gives you the charge 0. There's a significance to this, and we'll get to it very soon. Alright, let's look at an example. From the tables, you have at an anode is now, like I said, the reduction potentials, the reaction are written in form of a reduction reaction. So at an anode, what is happening is you have copper 2+ gaining these 2 electrons, which is equivalent to minus 0.76 as a reduction potential. That's for zinc. And for copper, it's plus 0.34. So this is what we have. We come to our table. For copper, it's here. It's plus 0.34. So the reduction potential for copper is what you have here. Then you go to zinc. The reduction potential for zinc is minus 0.76. Okay, so from here what we have is that since copper has a larger reduction potential, it will therefore undergo reduction reaction. Now remember, these are reduction potentials, and the reduction potential gives us a likelihood for a compound to be reduced. So if a compound has a higher reduction potential, what it means, it will undergo reduction. Then the one that has a small reduction potential will undergo oxidation. Then if it undergoes oxidation, so what you do is that when writing that chemical reaction, it will be written as a reverse of a reduction reaction. So for example, you have copper in aqueous plus 2 electrons, it gives you copper solid. This is the reduction potential. Then for zinc, okay, bear with me, I think this was not properly written. Then what you get is that for zinc, the reduction reaction will be zinc 2+ in an aqueous solution plus 2 electrons, giving you zinc solid. This is a reduction reaction. Bear with me, my writing is not very good. So this is a reduction reaction. But when we compare two reduction reaction, we actually discover that this reaction is greater than that. So in which sense it is telling us this reaction will undergo reduction. So if this reaction undergo reduction, so meaning this with a smaller will undergo oxidation. Remember, what we are looking at a redox reaction. So if one component undergoes reduction, then the other component undergoes oxidation. Then if it undergoes oxidation and you're using reduction potentials, what you normally get, it has to be written like as a reverse. So from the table, this is what you have. But when you look at the value, this is this, so it is quite small. So you are trying to establish that this will undergo oxidation. Then we'll change the reaction. So in oxidation, what we have is you have zinc solid giving us zinc 2+ plus 2 electrons as our oxidation reaction. So it is quite simple. There are two things or two parameters that you need to check. You go to your table. Now this table will always be given. The only thing that you need to understand is to know how to use it, but it will be given you in the exam. So when it is given you, you should just know how to apply and use it. So now what you get is that from here you get reduction potential. The reduction potential tells you the likelihood or the degree in which a compound will undergo reduction. So the higher the reduction potential, what it means that the compound is likely to undergo reduction reaction. The lower the reduction reaction, it means the compound will undergo oxidation. And if the compound undergo oxidation, then the chemical equation will be written as the reverse of a reduction reaction, like what has been shown in that point. Okay, different reduction potentials in a redox reaction. So what you get is that flow of electrons from one electrolyte to the other indicates the voltage difference between the two electrolytes. So let's look at cell potential. What we're looking at, these tables are reduction potentials. Now let's look at the cell potential. The reduction potential only concentrates or focus on one type of the reaction that is taking place at a half cell. But if you look at the cell potential measures the reaction that is measures the change in energy, and that change in energy mostly is given by voltage. So it is, the unit will always be V. So this voltage is the difference is normally called as electromotive force, and it is denoted by a capital letter E. Then E is measured by using a voltmeter. So a voltmeter is an instrument that is used to measure volts, and it also refers to as a cell voltmeter or a cell potential. So if the question is asked, what do you use to measure voltage in electrolysis? You use a voltmeter. Okay, then the cell potential E is a measure of how well a cell reaction can be pushed or push electrons through a circuit. Now, like we're trying to say here, or what this point is trying to say, is that one reaction is a spontaneous reaction and another type of reaction is a non-spontaneous. So what cell potential does is that it will be able to help us determine whether the reaction will undergo spontaneous reaction or the reaction will undergo non-spontaneous reaction. And from the definitions when we began, we described that a spontaneous reaction is a reaction that takes place on its own. For example, in what we have here, this is a spontaneous reaction. This reaction will only takes place on its own. So when you get zinc and copper, you mix them together, this is what will happen. However, if you apply an electric force to this reaction goes the opposite way, because a spontaneous reaction will move from this direction. So now what you get is that a spontaneous reaction move in that direction. Then when you apply external electric force, it forces the reaction to go that way, and that is a non-spontaneous reaction that you get. Okay, cell potential is measured in volts. Then volts are also equivalent to joule per coulomb. So these are some of the units that you look, or you will see as we try to start looking at some of the examples that we have. Okay, so this is the equation that you use to measure cell potential. So cell potential, basically this is with E. Standard cell potential will be equals to standard cell potential at the cathode minus standard cell potential at the anode. Now remember, what you get as a cell potential is the difference. So the electrical energy generated by spontaneous reaction is proportional to the cell potential. Then the standard cell potential is given by this equation. Then now what you get is that this is, since you say it's a standard, so these potentials were determined under standard conditions. Then the standard condition is 1 molar of the solution, then 1 ATP as the pressure of the gas, then 25 degrees temperature. Then a platinum electrode was used in a half cell reaction that did not include the metal. Now the platinum, you understand when we get to look at hydrogen standard potential or standard hydrogen potential. But all you need to know is that when you see a 0 on top here that looks like a degree, it means these are standard conditions. Then the standard conditions require the concentration has to be 1 molar for a solution. Then the pressure of the gas is being pumped in at 1 atp, and the temperature is at 25 degrees. Then from you have a platinum electrode. Now we'll get to see this as we proceed. Okay, so these are some of the examples that we will look at. Remember, so from what you get here is that this is oxidation reaction, and this is reduction reaction. So in which case what you have is that from this end you can write this is equals to, there's an increase in charge which is plus 2 electrons. Then if you look at the reduction reaction, basically what you get is you have this plus 2 electrons, so this is in aqueous and this is in aqueous. Then 1 electron goes to the platinum metal like this. So you'll be able to write these two reactions. Then when you say you write the net or the overall reaction, what you get is that you get these and put them on one side, and everything after the arrow you also put it on one side. So from here what you get is that you have ion solid plus ion 3 plus in aqueous plus 2 electrons, giving you this plus another 2 plus platinum solid plus 2 electrons, which is 2 electrons. So meaning these 2 electrons will cancel. This and this are the same, so we'll write it at the same. So overall you get this. I am trying my best to write this will be equals to, since these two are the same, so it will be 2 plus platinum solid. Remember, always include the state of those species. Sample question. Consider the following cell, right? You have this cell here. Now the question says sketch this cell labeling all essential components, then write the overall reaction for this cell. So you know this is where oxidation is taking place, and this is where reduction is taking place. So now what you get is that every solid will be on an electrode. That's easy way to see is that a solid will be on the electrode. So same applies, this will also be on the electrode. That's the easy way to note. So the solid will be on the electrode. So if we go to the next diagram, you actually discover that this is where oxidation is taking place, and this is where reduction is taking place. So all the solids will be the electrode. So the easiest way to determine on which one is an electrode is you look at the solid in the cell notation. So the cell notation will give you the electrode. Then the solution, in the solution you have charged particles. Then since this is what you have, so there is nitrogen that is pumped here, then it reacts with platinum and it gives you, so we'll get to discuss this in details as we proceed. Then you have barium ion, then barium chloride electrode. So this is what you get. So if you get to this, so these solids, this and this will be electrodes. So if you're drawing a cell, how do you establish which compound is an electrode? It is easy. Just look at the solids. So when you see the solids, then it will be able to tell you. So when you look at this solid and you look at this solid, it's able to tell you which compound goes to the electrode. Then the charges are always in the solution. I'm sure by now you understand, or if I can quickly go back, it says that an acid is any substance that give you a positively charged particle. So what you get is that a charge will always takes place in a solution or in a media. So when you look at aqueous, it means it is in a solution. When you look at aqueous here, it means you are in a solution. Then when you look at a gas, then a gas can only be pumped in through a tube, and that's what you're getting here. A gas is always pumped in through the tube. Then from what I've shown you, I think by now you're able to, you can establish, or you can write what the cell reaction for this compound is. From here you can write the cell reaction of how this compound is. Okay, let me, so now what you get from here is that you have platinum, so the platinum want to be there, of course, to be an electrode. The same applies as this, it want to be there because they'll be electrode. So what you have is only this and this in this case. So you get hydrogen gas. So this is oxidation. So you get +2. So since there's only one charge, there are two of them here, you balance by putting a 2 there. Then in this end you have barium minus plus these 2 electrons, giving you this as a solid. Then now if you look at this reaction, there's only one here, sorry, this is 1 electron. So there's only 1 electron. So now to balance up the electron transfer here, since there are 2 electrons and there's 1 electron, we multiply this side by 2. So you have 2b minus aqueous plus 2 electrons, then plus 2. Now the reason why we are multiplying by 2, it's simple, because there are 2 electrons and there's one electron on this side. So to balance up the electrons on both sides of the half reaction, we multiply by 2 in this side. Because you remember, if we said oxidation is the release of an electron, then you have reduction waiting for the oxidation to take place. So as much as oxidation will take place, much reduction also take place. So if 2 electrons have been released this side, 2 electrons have to be accepted this side. But if the cell reaction only release electrons, so meaning what means you have to multiply the overall reaction by 2 to give you this. So from here you can actually simplify and get your cell reactions like this. Let's look at or let's understand what's the significance of E0 or E value. It helps us to determine the spontaneity of the reaction. So it tells us which direction the reaction is going. For example, if E0 is greater than 0, what it means, the reaction is a spontaneous reaction. So the arrow that you use is it's a forward reaction. If E0 is equals to, if E0 is equals to 0, it means the reaction is at equilibrium. Then when E0 is less than 0, what it means that the reaction is a non-spontaneous and it's a backward type of, or it's a reverse type of reaction. I think we've spoken about this on how you determine the E0. So after you calculate the E0, you can actually check if the E0 is greater than 0, spontaneous reaction. E0 is equals to 0, equilibrium. Then when E0 is less than 0, then it tells you it's a non-spontaneous reaction. Okay, this is a typical or a practical cell reaction for the examples that we've been looking. For example, you have oxidation of zinc, then you have reduction, or you're using hydrogen. Now we'll understand this electrolyte, which is abbreviated as she, more or less like a woman, but these acronyms stand for standard hydrogen electrolyte. That's what she stands for. And mostly this is used to determine the electrolyte potential for different type of reaction. The reason why this is used, this is the reason. Let's get to our table. The reason why it is used is where is it? Okay, there you are. The potential is normally 0. So since the potential is 0, it can be used as a reference electrolyte. A reference electrolyte, what it means that when you connect, for example, when you connect a cell like this, then you get a voltage. Whatever voltage you get will come from here, because this is contributing 0. There is nothing. Then as you can see, these are the details that you get. So in here you have nitrite ion, you have sodium ion. They are helping the electrons to pass from one end to the other end. Then you have electrolyte here, which is zinc electrolyte. That's why oxidation is taking place. So you have half reaction. Then this is where reduction is taking place. Then in here you add nitrogen, then hydrogen. So when the hydrogen goes in here, it undergoes reduction, and this is the half reaction that is taking place. Then this half reaction is not generating any voltage. The voltage generated is 0. So since its voltage generated is 0, it is used as a reference electrolyte. Then it is normally abbreviated as a SHE, meaning standard hydrogen potential. Okay, let's do some calculations here. A cell potential is calculated by cell potential equals cathode and anode. Then from this reaction, we discovered from the table is that at the anode it's plus, so it's minus 0.76. At the cathode is minus 0.34. So when these two reactions are taking place, since there is a negative and a negative, this becomes a positive. So the cell potential of this is plus 101. Then from what we discovered there is that if this is greater than 0, this is a spontaneous reaction. So after you calculate the E0 and you discover it is greater than 0, meaning the reaction is a spontaneous reaction. It doesn't need any help to take place. It will take place on its own. Okay, oxidizing and reducing agency. The strongest oxidizers have the more positive reduction potential. So the strongest reducing potentials have the negative reduction potential. So this gives you, so what you have is that the most negative value of E and the most positive value of that. So as you can see, this is increasing going up to there, and this is decreasing going up to there. So for you to be able to establish, what you have is that the one with the highest positive charge has a high degree to undergo reduction. So the compound that is reduced is an oxidizing agent. Or this is what it means when you say an oxidizer. So a compound that has undergone reduction is an oxidizing agent, and it's an oxidizer. And these terminologies, most people normally get confused. So if a species undergoes reduction, it is an oxidizing agent. The reason why it's being reduced, it's because it's oxidizing another element. And what you get or you understand is that from now, redox reaction don't work. Oxidation reaction don't work in isolation. They'll always work at the same time with a redox. With a reduction reaction. So you would understand that a compound that has been reduced is a strong oxidizing agent. Then the compound that has been oxidized, right, is a reducing agent. Then now we can understand the degree. If the positive charge is very high, so it means it's a very strong oxidizing agent. So for example, if you go on this table, this compound is a very strong oxidizing agent. This compound is a very strong oxidizing agent. Then this compound is the least oxidizing agent. That's what it means. Okay, so it's the same thing that we're talking about. So for example, this is more positive. So this is a strong oxidizing agent. Then this is a strong reducing agent. So this is strong. This is a strong oxidizing agent. So it goes in that particular way. Let's understand what a She is and how it works. A She is, so this is abbreviated as a She, meaning standard hydrogen electrode. So a hydrogen electrode consists of a platinum cover. So this is a platinum plate with fine powdered platinum around the hydrogen gas is bubbled. So what you have a tube here, it goes there, then you bubble the hydrogen on this. Then its potential is defined as 0 volts. So the E0 for She is normally 0. So it is used as a reference point in most of the calculations. So this is actually a reversible reaction, but either ways it still gives you 0 for. So the best example that you can get is that you have on your oxidation, then as you can see, you have platinum. This is 1 ATP, this is 1 molar, and then at 25 degrees it gives you standard conditions. So I think we have looked at this. So now what normally happens that this reaction mostly is an oxidation reaction. So the E0 at the anode is normally 0. So what you get is that this, since when you're using sham, E anode is 0. So technically speaking is that the cell potential will be equals to the cell of the cathode. That's the reason why it is used as a reference potential, or I mean a reference electrode. Then she, okay, I think I've described all of this. So it is at 1 ATP, then 1 molar, then the voltage that you get is normally 0, and this is what you have. So this cell will be equals to 0. So the reaction can go either way. So it can either go to the cathode or it can go to the anode. Then either ways, what you get as your value is mostly 0. Okay, so you have a zinc half reaction with the She. This is what you have. So at an anode you have zinc half reaction, then at the cathode you have a She. Then here the E0 is normally 0. So the calculations that you get is that from here, this is giving you, or the standard potential for this is 0.76, because you have 0 minus 0.76, it gives you 0 plus 0.76, which is basically 0.76 if you're using a She as your, because you know this is the cathode. For E0 you have E cathode, then minus E anode. So the E at the cathode is 0 and the E at the anode is minus this. So that's the reason, or that's the other significance that you get to use a She. Okay, for this series of lecture, or let me say I'll end part 1 of this lecture here, then I'll continue with part 2 starting from an earnest equation. Thank you very much.